Okay, so for the people online, we will start in a few minutes. Taking place in physical spaces is longer than in virtual places. So people are coming in the room and they install themselves. In a few minutes, we will start. Okay, so it looks that locally we have an issue with the network connection. It will be solved, but that also makes you be more attentive to us. So don't panic. The network will come. Okay. Good. So I think we should start. Is 9:08 CET and some other time 08 all over the planet for the people online. So first of all, welcome to Web3D 2022. Welcome to welcome in France. Welcome to and to our school here, Telecom SudParis. I will not speak about the school. There will be some other people that will speak about the school. But first of all, in this welcome message, I will ask our director to say something about how beautiful we are in this school, and then Christophe will give you some overall indications about the conference, and I will then continue with introducing in details the program of the next 3 days. Monsieur Dellacherie.
My priority is excellence. That's why at Telecom SudParis, we teach excellence in the field of 3D and virtual reality. We want to train the best engineers to build the next Web3D. That's why we rely on excellence in research on this field. And that's why we are very happy to host this Web3D conference in Paris, in Telecom SudParis this year, with everyone here on site and everyone on web conference. So we want to combine the development of the metaverse with digital sobriety. This is very important to us. And we are seeking environmental excellence also for our children and grandchildren. That's why I'm very happy to see that we will have developments on this topic this afternoon. At Telecom SudParis, we are also looking for excellence in international cooperation. That's for sure. So I want to thank you all for being here to progress along this other path of excellence. Excellence in international cooperation, for Web3D, for virtual reality, for Metaverse, and doing sobriety, digital sobriety at the same time. So I will give the floor back to Marius, Preda, and I wish you 3 excellent days during this scientific conference. Thank you all.
Thank you. Thank you, François. So you understood, switch off the lights, switch off the computers to be sober energetically. Thank you. Okay, Christophe, who is our general chair of this edition of Web3D 2022. Maybe he participated at least at half of them, probably more, but he's long runner of Web3D conferences. So Christophe.
Thank you for your warm welcome, Marius. So I'm Christophe Mouton. I'm representing EDF, so the French National Power Utility. And yes, sober in terms of power, we know what that means when you are producing the electrical power for France and some other countries, European countries and other countries. So yes, Marius, I was lucky to be in 2003 in my first Web3D conference. So it was the one that was in Saint-Malo, first one in France. And I'm very lucky to see some faces that we already meet very long time also in Paris, because the Web3D comes in 2011 in Paris. And when the Web3D Consortium board asked us, would you like to welcome Web3D in 2022? We say yes. We were in lockdown. How we will manage that, we don't know. But we are agile, you know, flexible. And yes, and today we are there. So in Evry at Telecom SudParis, and also thanks to Vuva and Teams online through the world. So the topic is the trend one, so the trendy one, so Metaverse. I would like to remember that 20 years ago, it's quite vintage, we were talking about cyber world, Metaverse, something new, you know. So I think we are experiencing right now a new, I would say, stage on this work, and perhaps we will get furthermore, and on that topic. And I'm sure that the program that Marius will present you in a few minutes will interest you a lot. We have very impressive talks, of course. We will have a keynote speaker. So the first will be Nicolas. So Marius will introduce him. We will have also Mike Zida, a professor at South California University, end of the day today. And tomorrow we'll have an alumni from Telecom SudParis, so Marc Petit from Epic Games. So yes, we have some impressive talks, but also keynotes. I already mentioned them. We have also workshops, and we'll have one about Notre-Dame de Paris by the leader of the CNRS team. On how they use Web3D technologies and other 3D technologies to help to rebuild Notre-Dame de Paris, the Cathedral of Paris. I think that I cover a lot of things to introduce this conference. So feel free to get in touch during these 3 days. It's always a pleasure to meet together, and we can discuss on technical topics, but also on projects. So I'm very happy to welcome you at this 27th edition of the Web3D conference. Thank you.
We cannot hear the applauses of the other ones, but I hope they also did the same. Okay, let's have a look on the program. There, you have the information on the web, you have the information printed, but still the information may change with the time. But still, I want you to have together a look at the program and see how we build it. Okay, first of all, we received in terms of contributions about 50 regular papers, short papers, long papers, posters, contributions to workshops, and also standardization related side of contributions. We select for regular papers 11 papers that we grouped in 3 sessions. So there will be a first session of regular paper. Don't try to read, doesn't matter. What matters at this level are the colors. So the regular sessions are with no color. So we have just one here. Tomorrow morning at about the same time, we have another session for the regular papers, and tomorrow in the afternoon, a short one here. Each line is 30 minutes. So the experts in visualization will kill me because I show you that. It doesn't mean that the coffee break here is much longer than the others. No, it's still 30 minutes. But the text made this visualization. Okay, so in terms of regular papers, three main sessions with 4, and 3 papers. The first one is we try to group together contributions that are more on rendering and processing part. So this is what you will hear about in this morning. Tomorrow we are going here in this session. We are going more in the 3D content pipeline with applications as well. So AR, VR, and in the afternoon we reserved the contributions that were more focused on Metaverse itself. As you already heard and as you know, we chose the theme of this year, also Metaverse. Was not a surprise for no one. It looks that, oh, there is something new appearing, Metaverse. We all know here in this community that is not new at all, because many of us already worked 20 years ago on exactly the same problems as today. But it's good that people wake up from time to time to say, oh, this is new. That will put more energy in the cycle, and will have more technology, more knowledge to develop. So of course we will take that trend as well. Then the blue ones are the workshops. They are many and interesting. Unfortunately, we had to put some of them in parallel tracks. So physically you cannot be in both. Virtually you can be in both, but you will not understand anything if you just try to use your left ear for one and the other for the other. Luckily that we record all this. So later on, if you really want to have a look on what happened in the other room, you can play that workshop. Then we also have a tutorial in parallel with the first workshop in the afternoon. The last day is a particular day, because in the last day we have session of 2 hours here, the gray one on the top, that contains the posters, but is the fast presentation of posters. So every poster author will come here on the stage for 10 minutes presenting what the poster is about. You don't have the right to ask questions. They don't have the right to answer. But later on, in this slot here, the orange one, there are the interactive discussions. So we will go outside. The people that have poster printed, they will display them. Others will come with computers and demonstrations, and you have the right to put all the questions you want. Something similar will happen in the afternoon, but here we don't have posters anymore, but we have industrial use cases presentations. In general, proposed by industrial partners of the conference. They have demonstrations. Some of them will come with some screens, some others only with a computer. And same format as in the morning. We have 10 minutes presentation for each of them, such as people also online, they can have all the details, followed by an interactive session with questions and answers. Okay. There is something also on green that happens today and tomorrow evening. These are our sponsors. And we have to thank them, but we also give them the opportunity to speak about what they did nicely in the last even 3 years, because I don't know how much chance they had to communicate with people during the COVID crisis. So we'll have first sponsor today, which is Ariason, and then we will have tomorrow evening for us, but very early for them, NVIDIA with Neil Trevet. We also have keynotes, as mentioned by already by Christophe. Today in the late evening, so it's a very good moment to listen. Nice historical view is Professor Zida that will make us do a trip in the history of 3D graphics and Metaverse. And tomorrow morning we have Marc Petit. Centrally, here we have a panel. It is not usual to have a panel at the middle of the conference, but with all the arrangements, with a lot of people invited, this is the best compromise we found. And this is a panel about standardization. Let's not use the word standardization because that is a big word, but at least interoperability. So we will speak about the need of interoperability in Metaverse and what are the possible actions that can be done to put some interoperability. We know that it will not be easy. And before that interoperability panel, we have some presentations of standard-related contributions that may help us in going more in details on that aspect of interoperability. We have the lunch breaks. Lunch breaks for people that are in Evry are free. For people that are online, you have to find a sponsor. So the lunch break, the lunch is not far from here, walking distance 2 minutes. You only have to wear your badge, and there is a dedicated place where you can sit. You choose your neighbors to be the nice ones, but you are free to take any place there. We have coffee breaks, and we also this evening for the ones that are in Evry, the dinner is also offered. So by using your badge, you can go at the same place as for the lunch breaks, and you have the dinner. The last one, but not the less interesting one, is our social event. Luckily that we had some support from sponsors, so we can invite you at the social event. I should say that twice for the people online. So we can invite you people here physically at Tour Eiffel, or the restaurant of the 4th floor of Tour Eiffel. The food is good, but the view is just impressive. So I really hope you enjoyed it. And at the end of the conference, of course, we will have the award. We have the Age Anim Award that was already, so we got submissions for Age Anim content with some 3D nice content videos. We will display all that, and we will congratulate our winners. And we will end with our award ceremony for the best papers that were selected for the awards of the best papers. Okay, so on the website you have this this picture is also printed, but for sure, if you want to go in details, you have the detailed program with all the information. Okay, any question? Some changes that you want to see? because you have some constraints, the train going, no. Question from people online? Yeah, they are not allowed to speak, they are only allowed to write. So Zied is following the discussion, no question, no. Good. Then I think we are done with this introductory section. And we are eager to hear you, Nicolas. So we will go in our program and start with the first keynote. You all know Nicola Polis. Maybe he participated to the first Web3D conference. I don't know. I was not there, but he will tell us his story. So Nicola is director of visual computing with Virginia Tech, and he is maybe the one created one of the first 3D interactive system back in 1997. So he is old, but still in good shape. Okay, so I suggest to do the switch and install Nicolas here. Yes. Anita is telling me something. Don't.
The wired one? Okay, super. Thank you so much. Good morning, everyone. It's a great honor to be here with you this week, and a great honor to be invited to provide some of my perspective on this great industry and all of the activities of our community. As Marius mentioned, 1999 was actually my first Web3D conference in Paderborn, and met many great folks, and it set me on to this path, which I'll tell you some stories about today, and a little bit of perspective. So I do want to thank our hosts again, Professor Patrick and Marius, Christophe, Mouton, thank you so much. So I will try to provide a little bit of, my perspective, not only, what's behind this new cycle, but maybe as a good keynote should be to kind of look ahead a little bit and offer some ideas about what are some key issues for us to work on as a community. So there's also another title here, although you may be expecting lots of engineering and technical positions, but actually I was thinking maybe there's a question that's a little bit bigger about our evolution, really, as a society. And so I'm going to challenge us, I think, this week with some ideas that maybe are central to making progress. So, I have been living in the time before cell phones, the time before the technology that we take for granted so much today. And I think this gives me some perspective. But also having the experience of building 3D virtual worlds for many years and seeing them sort of come and go. And I think that's one of the things that I would like to sort of start with is this has been an ongoing project, right? We're still not there. And as Marius mentioned, we have new opportunities today. But I hope that you'll just take this as some perspective and my experience. So many things have happened, obviously, in the 20 plus years of technology and the web. And we've unfortunately seen a lot of patterns of cycles of where we all get very excited and we make some new companies and, oh, well, maybe that product line is done or the company is done. And all of that great content disappears, okay? And some of you may remember something called Flash once upon a time, great example. But this is sort of a lesson where, maybe the power should be not just in one company's hands, okay? And look, I don't want to not point fingers. There's plenty of shame and blame to go around about why we have not made such good progress over the last 20 years. That's another talk, okay? Because meanwhile, we've had decades of getting real work done with 3D on the web, and real productivity, real scientific discovery, okay, real design, and interaction. And so this is something sort of parallel to the narrative that maybe some of the marketing would lead you to believe. And yeah, it's a little bit ironic that undergrads can build this sort of thing, but big companies can't seem to figure it out. Okay, so let's think about what some of this might be. We do have major progress, and we should recognize this, right? Great engineering advances, certainly in how we're tracking our devices, viewpoints, rendering 3D graphics with good frame rates. We also have this huge web of information systems, right? We can compose data, present it across all sorts of platforms, and that's really called the web. But another thing that is perhaps more fundamental as a change is that we're carrying around computers every day, and we have networking. And this sort of opens up a new possibility that maybe it's not just virtual worlds, right? But there's something about physical and digital life that we need to think about. Of course, there is some money on this round as well. So a quick look ahead. I'll treat this a little more as I go forward, but we are thinking maybe about what is it to live in such a metaverse, and many people will have different ideas about what that is. I'm going to make a case today that really it's a social and psychological problem. It's not an engineering problem. And some of the things that we know we have in the real world that makes society work, right? We have citizens who have agency. They have protections in legal form, and they're working on a common infrastructure, our roads, our telecommunications. So I just wanted to share this, and this is a positive talk, believe me, but as you might be able to read, but this cartoon I enjoyed. Those who don't study history are doomed to repeat it. But those who do study history are doomed to stand by helplessly while everyone else repeats it. It's a little close, but it should be funny. So what's driving these ideas? One of the first things, and I'll give a little history here and try to be quick, but certainly we had a transformation in the media once upon a time, right? And going from the stories around the fire, okay, to a book where we could actually reproduce the worlds that we were making, right? So those words are the same words that I read, that you read, that our children will read. And this is the first kind of reproducible world. Of course, we see this transformation happening over history, lots of different media types. The print was just one, okay? But certainly the communications all the way through the radio has changed the fabric of our society, how we work, how we do things together, and communicate. So this isn't new, of course, but we started to think about what is obviously the technology, right, that will enable such a presence in the digital world. And I wanted to share, 1968, there's a great little video, it's short, but you can see that we've been working on virtual and augmented reality for a long time. Okay, 1968, Sutherland's actually was, I would call it a augmented reality system, if you watch the video. But these are decades ago now, right? Okay, and as technology has evolved, right, we started to come up with some new words, new ideas, and certainly cyberspace was one that dominated the 90s, especially. Video killed the radio star, another example of media transformation, a little bit lighthearted, but you might like the song. Once upon a time, there were a set of releases. I don't know if it made it to Europe or not, but the Mind's Eye films, and I don't know if anyone's ever seen these, but this is some of the original computer graphics and rendering music videos from the 90s. And indeed, I'll just keep going. They made several of these. This one has a great soundtrack by Jan Hammer, so it's worth watching. And then it wasn't just about you know, buying a VHS with these movies on it, but we started to build worlds that were interactive and shareable. And I can remember one of the first things that got me excited about this was a platform, I believe it was from Canal Plus, if I recall correctly. But I was on a 28.8 modem, dialing in and flying around France Paris with an avatar, meeting people and chatting in 1998. Okay. This was a metaverse. It was shocking to me. I was amazed. I made friends, you know, we were waving, chatting. And so over the years, right, there have been systems that we could really call metaverses, right? We have a digital presence in this shared world. And there were several kinds of platforms sort of enabling this, all the way to Sony, if you remember. So as that excitement was building, you know, a number of online communities grew up, such as Colony City or Cybertown. These were built again with the web in mind. They were built in VRML. You can see we have sort of the typical kinds of components here in the user interface, right? Our 3D world, chat logs, different participant views, and various ways to interact and communicate with the folks in that space. What was interesting here is there weren't a lot of rules in these early worlds, but certainly people started to sort of self-organize, and we began to see things like guilds and even political systems growing naturally in these worlds. So then we became, there was another round of death and rebirth, and we had a whole series of pretty compelling products, right, in the mid-2000s. And even the federal government of the United States tried to find some kind of platform, right, for their virtual worlds. And unfortunately, you know, none of these worlds could talk to each other. And you couldn't move your avatar or any content from one to the other. And this, I will claim, is a very key aspect of why these systems have failed. And lots of money, they're all gone now. So let's do a quick thought experiment here. I'd like to see a show of hands, if I could, please. So let's imagine some parts of the metaverse, okay? And let's think about maybe some transportation. Like, let's have you imagine a car in the metaverse, okay? So let me ask you a question. I'll see a show of hands. Whose car has lights? Okay. Lights in the front? Lights in the back? Okay, red lights, white lights. How about a steering wheel? Anybody have a steering wheel in their car? Okay. How does that work? It turns around an axis, yeah, when you manipulate. Does your car have Um, sorry. Does your car have wheels that turn? Right? They turn a certain way. Okay. Now these are interactive aspects of these models, right? These are models that have lighting properties as well as materials and geometry, right? Okay, so I want you to think about that. Now let's do one more. I'm not going to say clothing, maybe a bag that you might travel with in the metaverse, maybe. Okay, so does your bag have a zipper? Does it have a clasp? Okay, these again, all are interactive properties of the object that need to work whichever microverse you're in. Okay, and this is one of my claims. Okay, so we need a definition, and we do, I think a lot of us here kind of can start from this beginning spot where we have real-time scenes, their lighting, interaction, objects. We're composing worlds from lots of different assets, maybe from different places in the network, right? We're delivering that, presenting it across lots of different platforms. And we're sharing the events that happen in that world to all the participants, right? This is that multi-user networked aspect of the metaverse. And so I wanted to, I would like to share a little example from my work. My first 3D world, right, in 1998 was the Giza Plateau. We used GIS data for the terrain, you know, digitizing drawings from archaeologists and making an interactive place to go and experience, in this case, music content. Similarly here, now 12 years and running 3D city models, okay? And not just using GIS and BIM and terrain and even architectural, you know, design tools like SketchUp. You might see some nice textured buildings here. But those can then be inhabited, right? With people, cyber citizens. One of the things that is probably important about the interoperability, right, is that this content can be moved across different systems. So this example here, again, we're looking at the same lighting, interactivity properties of an environment, using it on different servers, using different communication protocols. Okay, an interesting proof of existence for Metaverse. I mentioned the students and undergrads, and I'm very pleased to have some papers of and work of theirs to present later. But our senior group, they were able to prototype a concept, build it, and test it, you know, in one semester, because they're using web technologies and X3D and GLTF, for example, for 3D technologies. And this is something that is still true. In the 2011 edition, I gave a tutorial called Building Networked Virtual Worlds. And yeah, I went back, I checked it out, and indeed, this is all still true. So what's going on lately? I guess I would say that, you know, there's never been a killer app for 3D. We know that it works well for lots of different verticals and applications. And indeed, you know, 3D is ubiquitous now in almost every industry. So, but these are silos of excellence, right? They don't necessarily play well with others. And that's where we'll get to discuss throughout this week's program, right? How we can build kinds of platforms that aren't just fragmenting our digital life, but somehow can unify it, right? And support new ways of communicating. And of course, more recently, you know, some of the ways that the web has gone are problematic, right? The ad tracking, the monetization of your activity and behavior. I don't believe this is something that the metaverse can support, or that's not going to be core to the metaverse. So is this going to be just another, one-off, another ad tracking environment? These are questions. Are they going to be special? Is the metaverse going to be specialized for tasks? Like if I go from work to home, hanging with friends, colleagues, I already have more passwords than I can remember. I don't need more fragmentation and much less yet another device to track. So something has to be seamless here, and that's the interoperability story. I also like to say that some key things are blocking us, which is blocking consumer adoption, right? So the protection of data, the ability to remove oneself at any time, right? To take my data back. And we need to kind of build up some cultural norms about what's acceptable in this as digital citizens. Okay, well, there might be a lot of explanations for this. I'll just share a few from my experience. There's a sort of mentality of academics and venture capitalists that, oh, it's not invented here. It can't be good enough for us to use. There's also what I call the Highlander pathology. If anyone's seen the movie The Highlander, it's a little obscure and silly, I know. But one of the key plot drivers here is that there can be only one, right? As if someone could own the web, or some company could have a monopoly on this metaverse. I don't think so. Lastly, when you have these cycles of market hype, consumers, it never lives up, right? So in a certain way, we're ensuring our failure by hyping this stuff. So is it business as usual? What I'm recommending here is that maybe we think a little differently. Leave that behind. Try something new. Okay. So do we have an appetite these days to try something new? Right? And one of the things that I look back at all of the cycles of failure, and again, what we need to be able to think about is the payoff, right, worth the effort now? And so if you haven't baked the pie, right, it's not going to be very good. We've seen for years how innovation can happen on top of standards. Okay, and that's sort of the model that I would like to propose. So a few things ahead. Clearly, we need to provide some more protections for your data and behavior in this metaverse. There are always going to be bad actors, okay? We've seen already there's lawsuits against Roblox for not protecting minors, right? The first 10 minutes of Facebook's Meta, there was a sexual assault, okay? They had to change the algorithm of proximity and things. So how is this a surprise? I'm not sure. So we have challenges, but maybe some ways that we could approach. Maybe real world citizens, we have rights, right? We work on common infrastructure. Are there some lessons we can take to apply to the metaverse? I don't believe it's a game. It's something that is perpetually evolving, right? And again, it will lead into all aspects of our lives. I don't know if folks have read Jerome Lanier, one of the original pioneers of VR. Great book called The Siren Servers. No, Who Owns the Future is actually the name of the book. But what if every company who is using your data had to give you a little bit of money back? A royalty scheme, if you will, micropayments to use your data. It's an interesting thought. But all of this leads again to the fact that I don't believe technology is the blocker, okay? And we're going to see amazing stuff this week, including new capabilities from the ISO standards of X3D4, the new World Wide Web Consortium standard of WebXR, right? We have these today. We've seen in this conference and even the last edition how using web audio and X3D for virtual environments. Oh, well, now I can spatialize my audio and I can hear someone's talking over there, right? This is a very important piece for that presence. We need to be able to find interoperability across the web, and this is again where our work is cut out for us. Looking for device independence, and not just to talk about presentation and interaction, but the connectivity, right? We also have a concept called net neutrality, right? So again, I'm trying to put the concept that the citizens, cyber citizens, should have these rights and maybe should be the focus of our design. So I think that's probably getting on the time for me, but I do want to say a few takeaways. Let's learn from the past. You know, these things are not just buzzwords. If we're looking for long-term wins, like sustaining an economy, an ecosystem that's productive, allows lots of people to be included and participate, these aren't buzzwords. This is more of a philosophy about the metaverse. And finally, I am thinking about this idea, which is maybe we take some of those citizens' rights from the real world and we write something for our digital life. You know, a declaration of digital human rights might actually be something that could give those consumers confidence again to participate, okay? And maybe also for industry to behave well. So thank you again for your attention today. I want to welcome you all to the Web3D community. You know, we have a wonderful process of developing technology as a consensus-based process. We have standards and technologies that have stood the test of time, running faster than ever. I'm still challenge anyone to show me a demo older than 20 years. And proven people, which is what we're here all together for, is to meet each other and make connections and discuss these ideas. So welcome, and I hope that you'll join us. My contact information is here, and I'm looking forward to our conference together. So thank you.
Okay, thank you. But since we have some time, maybe we can have some discussions and question. Yeah, indeed.
Super. Yes, please.
Thank you so much for your presentation. I'm very interested by this idea of social interactions in the metaverse, but also with the social interaction between the human in person and the virtual world. And of course, we need to have new laws and rules about how to behave. For example, can you just cross the avatar of somebody else and say, excuse me, I've just crossed your avatar, or do you need a bounding box and exclusions of people if they are not behaving well? So do you have ideas about these 2 points inside the metaverse and between the metaverse and the real world?
Thank you. That's a very good question. Very good question. And a difficult one, I think. So I guess what I'm advocating for is for us to consider, again, socially, what kind of norms we want, because this is a chance to invent this, right? We have very little baggage, right? That's maybe another good point about all of those dead products. We can maybe start anew. So yeah, are the cultural norms there? And I don't think we have them yet, honestly. Often we're working in these, what we were calling sort of microverses. So, you know, a company, we won't name which ones, you know, but you're in their platform. And so they're going to write the rules of interaction, and the norms of behavior will also be written by them. And I think this is the place where, again, I don't think it's a technological problem. Yes, we have technologists will need to be able to, you know, ensure or find ways to have, you know, an open platform to make this performant and secure. But I think the challenges aren't so much technological anymore. So what are some ways we could do this, I guess? Certainly education is where we start. As a professor, I'm bringing these issues up for discussion amongst all my students. There isn't a right answer, I think, at least not yet. So it's an ongoing dialogue. I do believe that something like a guiding document would be helpful. So this idea of a digital bill of rights, we're seeing similar protections starting in the US as well. I don't know if folks have seen, Biden just released a human and AI rights document. So how is AI actually going to respect these rights of citizens? It's still very much prescriptive. There's no law around it. There's no mechanism to enforce it, right? The Bill of Rights is just a document. But what we do with it, how we make it operational, is something that's going to need the whole society. And so I hope that we can have that dialogue and also to sort of break out of just this technological view that if we make, you know, faster triangles, it will be better, because it's not really what's holding us back anymore, in my opinion. But thank you. That's a great question.
Good. Thank you. Anita, yeah, I think yes.
Thank you, Nicholas. That was a great presentation. I shouldn't be really asking questions, but I will, because Nicholas and I are colleagues here. I have two questions. I think AI is going to play a very important role in the metaverse. How do you see this being integrated with the 3D digital world?
Okay, so yeah, I agree. Well, this is a sort of an interesting phenomenon, right? We had started with the idea that we would just totally replace our substitute for our senses with virtual reality, right? We'd have the sensorama, you could be there, smell it, see it, touch it, right? All of these challenges about presentation to the senses. And in a way that was easier, right? Because it was a specific place that was didn't have all the diversity that the real world has. But I do believe that if we're walking down the street, right, and I'm talking about the car of the metaverse or your handbag in the metaverse, these things are accessible, and this is really the bridge between your digital life and your physical life, right? So how these so we can, you know, we can render the fine automobile, right, in virtual reality, but now we can do it also in augmented reality. And so we all have our unique perspectives on this existence. But with augmented reality, we have also this, the physical life. So it's a little bit more of a challenge maybe than VR was, because VR could be anything, but AR is limited by our reality here too. So I believe there should be seamless. I guess maybe to answer the question a little bit more is that 3D content, it should matter where it comes from. It should be, you should be able to trust it. You should be able to know, you know, maybe where it comes from, what the rights are for it, how to share it. There are some things we can learn from history, like the idea of why do we always have, you know, avatars making trouble in the metaverse? There will be ugliness, there will be challenges, right? But I think the hope is that we can build bake the pie, right, before we start to slice it up. And if that happens, then we'll all be able to use this bridge and have some confidence in that we're safe and protected. Was that the first question or the second?
Okay, the second one is you said that the metaverse will be a family of microverses.
Oh.
How do you see us going from one microverse to another without dropping out of 3D?
Mm-hmm. Great question. So yeah, the seamless aspect of this physical and digital life. You know, I've been arguing against the fragmentation and the Babelization of the 3D content because that's what keeps you in a microverse. Well, I can say that my hope is, and the reason that I'm working with the Web3D Consortium is because I do believe that it needs a community to develop it. And so it's not just going to be one solution or one standard even, you know, we have to realize that it's an ecosystem and and basically that we can't have one winner will take all. So I think we do need to spend our time on these kinds of standards. We need to understand their pros and cons, right? How they were good, how they were bad, and sort of elevate the conversation a little bit. And so I'm really happy that we get to work in the consortium like this and having touch points with all kinds of different industries, right? So being able to touch the CAD and BIM standards, being able to touch medical health record standards, right? We need to find a compatibility between these things if we're going to use them in a new productive ways. And I do think that has to be some work in terms of standardization. So that's my hope.
Great. Thank you, Nicolas. And
thank you.
Thank you for the questions. We are out of time. But Nicolas is still here, and he will have other time. Okay.
Okay. Yes, we'll talk after the session.
Yeah.
Thank you.
Let's not try for the first one to take longer than it should be. Okay, good. Thank you very much, Nicolas.
Thank you so much.
It was great to hear from you. So now we are starting our first regular paper session. We have Professor Indira Tuvnong, who will chair the session. So we invite the first speaker, but I let you run the show.
Thank you. So the first session, I'm very honored to be the chair, will be focused on the visibility of the metaverse. So this invisible world is existing, and we have all work, and we know that we need lots of models. So I would like to invite the first author, Lukas.
I will show you how to do it. So yeah, I will say it once for everybody. So the speaker will be connected on Teams and share the screen. You don't need the cables, but just share your screen on Teams. So he will come here, and so if you want to stay there, and okay.
So Lukas Wagner will talk about hardware accelerated rendering and web-based 3D scatter plots with projected density fields and embedded controls. And I want to welcome all of you for the first session, including the non-visible participants also.
Thank you. Hello, I'm Lukas Wagner from the Hasselplatte Institute at the University of Potsdam. Today, I want to talk about our technique on solving occlusion issues in 3D scatter plots and how we implemented this in a web-based renderer using WebGL2 and what issues we faced doing this. Let's first look at the advantages a 3D scatter plot provides. First, the mapping of the data to 3D coordinates is really intuitive for the viewer. This matching from data points to physical 3D coordinates leverages the inherent human 3D understanding. We are used to viewing things in 3D, so leveraging this is really useful. Such a render is really versatile. You have multiple visual components. First, the 3D coordinates, obviously, but also data point size or color. And you can match any arbitrary data columns to these visual variables. And lastly, all this can be done really performantly on the web using hardware accelerated rendering, as well as, for example, techniques such as instance rendering. This can be done really quickly. In a past contribution to Web3D, we showed our renderer shown on the side here, which is capable of handling tens of millions of data points using consumer-grade hardware, and all this with interactive frame rates on the web. So that sounds all great, but what are the downsides to this? Well, when you... Sorry? Okay, sorry. So when you extend the scatter plot to 3D, you introduce the issue of occlusion. So data points can, from the point of the viewer, be occluded by other data points. And in the worst case, they will be surrounded on all sides by other data points, which makes them practically unusable to the viewer, to the user, as you can't interact or see them anymore. And this, of course, is a well-known issue in 3D rendering. Occlusion is like the issue for things. And let's see how we could solve this. Well, the easiest solution is just hide what's occluding other stuff. Sounds easy, but doing this automatically is a hard process. And usually when plotting data, you don't want to do this automatically because, well, maybe you're hiding stuff that the user actually wants to see, to make him see other things that he's not interested in. So we decided to give the user the authority on what he wants to hide. And one easy example of this for this is using cutting planes, which are just planes placed perpendicular to axes, which the user can slide around to hide data. For example, in this case, we have one horizontal cutting plane, which the user slided down using this handle on the left, hiding everything on top of it. So like in this comparison here. But these have to be placed manually, and finding a good configuration may take some time. So how can we give the user a quick look into the data set so this can be accelerated? For this, we decided to add density maps to the scatter plot. These are placed on the grids, which are seen behind the 3D scatter plots, and are some X-ray-like 2D views. These are projected back there, and because these grids are orthogonal to the main axes, these can be seen as the front view, side view, and top view from an architectural drawing or something. So it gives you like 3 axis-aligned views of the 3D plot in 2D. So now that we have these plots, and we will get into how we build this later, how can we connect them to the plot, to the 3D plot? Because right now it's just some more plots on the screen. How can we connect them? So for this, we added reference lines, which connect from the data points to the backplane. So for example, you can choose one point to inspect, and it will give you lines to where this point falls on these density maps. So here on the left, you can see that this point is in a cluster on the right as well on the left. And so this is at some hotspot in the dataset. Or inversely, you could place reference lines on a density map to filter out any data points that are close or related to this cluster. For example, we on the right image, we selected the cluster on the left, and now we filtered for the data points which are close to this cluster to analyze them later. Let's see a quick demo of this. Let's see if I manage to switch my screen. I guess I have to cancel sharing first. Yes, this works. Great. So here we are in our viewer, and we have this data set here. Let's first, I guess, increase the point size a bit so it's all better visible. Yeah, that looks great. So now we can see our data set here. We also already see our density maps here. Let's just increase the grid offset a bit so we can see them better. And now to make it stand out a bit, let's increase the density, the strength and the gamma of this. So now we can already see some clusters or hotspots where multiple data points are located. So for example, we have this cluster or this cluster. Let's focus on this cluster for now. We could, to see which points connect to this cluster, we could, of course, try to see these points here or hover over these points. Okay, that looks great. All these are kind of in this cluster, but what is obviously easier to just add a fixed line here. And now we can look around. That's not what I want. So we can look around and introspect our points. And to filter this down even more, I will just slide down the cutting planes. So these are axis aligned as well. So we can already just see, okay, if we want to look at this point, we just move the slider to the grid locations. And for this axis, we will just do the same. So let's do it like this. And now we have singled out the data points which are related to this cluster. Okay, if we want to keep working with them, we could, for example, select them using a lasso tool. And if we now reset our cutting plane positions, we still have our points selected and could start working with them later. And that's a quick demo of our tool. So let me get back to the slides. We want. All right, back to the slides. So now look into the behind the scenes a bit. Well, of course, this isn't a completely new technique. This combination of two axes to build a 2D scatter plot is based on scatter plot matrices, which is a well-known technique for plotting multivariate data sets. And also embedding this in a 3D scatter plot is also available in some existing viewers. So, but what it doesn't look out for is the issue of overplotting. Because if you have too many data points plotted on a 2D plot, all these overlap and you can't distinguish them anymore. And as a quick reminder, we're working with like tens of millions of data points. So at that point, it just becomes a huge mess. And the solution for this is not plotting each data point individually, but instead render a density map. So to do this, we have to run an algorithm called binning. We separate these data into bins. And of course, this would be possible using a CPU side algorithm, but because we're hardware accelerated, we can do this using the GPU as well. So instead of Using the CPU to assign these into bins, we just render we render a texture, which is then our density map. For this, we first have to project our points to a 2D plane. So for this, we will use an orthogonal view matrix. And then we will have to, when plotting the points onto the grid, we will have to calculate the distance to a point to generate these gradients you can see here. Because we want to know how close a bin is to the center, or for each bin point effects, we want to know how close it is to the point center, so we can have like some smooth gradients. And for this, you can choose any distance function you seem fit. We chose a linear distance function because it gives us accurate distance. But for example, you could use an inverse falloff, which is used when rendering metaboards, for example. So this is a well-known example as well. And the last step is to add up for all points and all bins the how much a point affects each bin. And that's the hard part here, because, well, it would be easy to just use additive blending, but that's the issue we will face in the next step when trying to store these density maps. We need additive blending to make this go well with hardware acceleration, but this introduces some issues, yes. So for storing, we want to store them in a texture. The quick idea would be to use the stencil buffer. Well, it's meant to store or count data. So, well, we're counting things. But in WebGL2, it only has 8 bits of precision, so that's not enough. The most precision we could get would be using integer textures. For example, 32-bit integer textures, which would be great. But WebGL2 does not give us any blending when using integer textures, not even additive blending. It just, every time you render a new point, it just overwrites what's already in the texture. So that's not usable for us. So we are left with floating point textures. Later in the pipeline, we will want to embed these density maps into the scene. And for this, we need texture sampling. And we would like to have linear sampling there to hide artifacts introduced by low resolution density maps when choosing the bigger bin size. And for this, we would use like linear filtering. But again, this isn't possible in WebGL2 for 32-bit textures at least. So for now, let's see how far we can go with 16-bit textures, which both feature additive blending as well as texture sampling, linear texture sampling, and how far we can go with the reduced resolution precision. So these half floats, 16 bits, use 10 bits to store the mantissa, which, by the way, so how floating point numbers are stored, this gives us 11 bits of precision, or just about 2,000 distinct values. So to calculate how much data we could handle, let's think of some numbers using a 512 by 512 pixel density map and a point size of 5. We could estimate, and normal distribution, which is a pretty bad case as just one huge cluster in the center, we could estimate about 0.04 of points affecting the center bin, which isn't too bad. Now for adding up, we also want some precision, some decimal precision points, because well, we have a fall off, right? So we don't always have like a 1, a 1, a 1, but maybe the influence is just 0.1. So let's say we have a target precision of 0.1. We want 10 steps of precision. So this would mean we could store about 200 points in one bin before we could expect some loss of precision. So combining this with the 0.04% of points, we could expect around 500,000 points in a plot before we can expect some data loss. So this works fine for most cases, but again, we want to render millions of data points. So yes. Okay, there's some feedback. Sorry. So how can we fix this? Or how can we increase our possible data set size? Well, the obvious solution would be going back to 32-bit floating point textures. This would, with the same calculation, allow us to render 4 billion data points, which is, well, more than enough. We actually run into other issues with Web3D at this point. For example, the instance ID for instance rendering can only store 4 billion data points, since it's a 32-bit integer. This would, however, require us to implement the linear filtering for ourselves or by ourselves, which, to be honest, isn't that hard and doesn't impact the performance too much. So this would be the way to go if you need more than 500,000 data points. Or if this still isn't enough and you need even more data points, you could distribute them onto multiple buffers. Just add multiple render passes. You distribute the points, for example, by the instance ID, and all these buffers are then combined during an additional post-processing pass to build a single density map. And this can be scaled pretty much as far as you want. So this technique can be extended practically limitless. So now that we know we will store them in a floating point texture, we can think a bit about optimizing binding points. Well, we have 3 maps because we have 3 combinations of main axes. And so we will just store these in a RGB texture. On the left, you can see these 3 combinations. And on the right, you can see the overlay of each other in the final texture. So this allows us to just bind one texture in the final shader for reading this during the rendering pass, and which gives us a bit of leeway when using additional textures. So putting it all together, we have the grids on the bottom left where the density maps are plotted onto. We have, for example, the data points and reference lines all done during separate rendering passes. And putting it all together, this gives us our final plot. So lastly, let's check out the performance impact this this technique implies on the rendering process. Well, first, let's compare to the main rendering pass. The rendering pass that plots the points to the screen, which, as I said, is done interactively as an interactive frame rate for millions of data points. So in comparison, how hard is it to render these density maps? Well, first off, you have a much reduced resolution. You don't need a huge density map when plotting it onto a part of the screen. So, for example, you could use 256 by 256 pixels instead of the full HD, which gives us a reduction factor of over 30. On top of this, the shaders for rendering this, for both the vertex and the fragment shader, are mainly much more simple, which gives us another performance boost. And on top of this, we don't even have to render the density maps all the time. They only change when a new data set is loaded, for example, or if the user chooses to plot a different data column onto one of the axes. So this doesn't happen often. So for one, the rendering pass is really quick. And the second, we barely ever have to run it. So in total, there's no significant impact on the rendering performance. So finally, yeah, if you want to try the demo just for yourself, there's the link down there. And we also put all our code on GitHub, so you can check it out if you want. So thank you for your attention.
Much, Lukas, for your presentation. Do you have any questions?
Does this work on like videos and things like that, or you're just for scatter plots only? I mean, if you're doing rendering and you're doing rendering of cloth, how would you implement this?
Well, this is mainly designed as a data analysis tool. So I guess not on the video itself. You could surely analyze some video data when, well, you could. Well, it depends on what you want to find in your video when you want to analyze it, I guess. So you could, for example, use the time as one axis and the image as the other both axes, and then you have like the colors on the data points. And maybe you could try to find out something there, but that really depends on the use case. It's not designed to like handle video, but to analyze data sets, yes.
Thank you. Great work. This is really useful for a lot of scientific and engineering applications that I see a lot. In terms of the binning, could there imagine some other mappings besides the linear that might give you, a different result on the projection? So, in medical imaging, we have a maximum intensity projection or other algorithms that would govern sort of the density map. And you mentioned that you're using the linear ones. Are there other places or other functions that might be useful, do you think?
Yes, thank you. So one thing I mentioned were the metaballs, which would give us a much steeper cutoff. So we would have clusters which are really sharp, which would probably help as well. So you would have to slide the gamma and strength sliders a bit more to have like a good result, because right now you have more steps of gray, so you can see more. But when you use, for example, inverse fall-off, you could have like really sharp clusters, which of course would be really useful as well.
Yeah, that's great. And you have controls for that in the web application. Yeah. So great, thank you.
Other questions? I have a small question. What are the parameters that you can use for your plans? Because I remember a very old project with the workbench. Maybe you know this, with the 3D cubic mouse, where you could use a cubic mouse to interact with 3D models and to render in real time some parts of the model. And do you use your planes as, I mean, they have to be always controlled with some speed, or what is the speed of the interaction of the plans, for example? Do you have a limit for?
Sorry, I didn't quite get the question. So you're talking about like interaction with a mouse, right? So
yes, the cubic mouse was a very, very old project where you could use some plans, but you had a device. Maybe you know, because it's close to your lab. And the cubic mouse was the device to interact with the virtual 3D models. It was not with clouds, but it was with 3D models. And you could interact and visualize and render. And this idea is very interesting too, because you can connect devices. And how can you choose your planes? That's my question. It's already pre-processed, or?
Oh, you mean which axes are plotted?
Yes, yes.
Oh, so yeah, that's just when you load a data set, it will try to figure out if there are any useful data sets, if it has like an X, Y, and Z coordinate already. Yeah. But you can freely select any numerical values to be plotted on any of the axes. And this is a drop down in the viewer. So you can, if you have like a 10-column data set, you can choose what to plot.
Okay. Very interesting. Thank you very much again. And now the second presentation is online. So et c'est qui présente? Le nom, mais le nom du speaker. Moonsik. Okay. So the second presentation will be a video presented by Moonsik Park, and he's connected and he will answer your questions after the presentation.
Paper. Hello, I am Moonsik Park, the author of the paper InstantXR, InstantXR environment on the web using hybrid rendering of cloud-based NeRF with 3D assets. I am thankful to have the opportunity to present my work to you here today. A little bit about me. I am an undergraduate student at the Catholic University of Korea, majoring in computer science. I had an opportunity to be a research intern at the Korea Institute of Science and Technology, during which I've done research on this subject. Currently, I am working as a software engineer at EastSoft Corporation. My research interests include neural rendering technologies and their applications. Research in novel view synthesis using neural rendering has been more than flourishing these days, especially after the debut of neural radiance fields, or NeRF. NeRF is a method for synthesizing novel views of complex scenes by optimizing an underlying continuous volumetric scene function using a sparse set of input views. It synthesizes views by currying spatial location and viewing direction along camera rays and uses classical volume rendering techniques to project the output colors and densities to an image. Although the ability of NeRF being able to render novel views of a scene photorealistically is groundbreaking, when NeRF was first introduced, it was too slow and compute-intensive for use in real-world cases. It took several days to optimize NeRF to a particular scene, and took several hours to render a video with novel views. There have been attempts to speed up NeRF. NV Labs released their NeRF implementation, which used a multi-resolution hash table of trainable feature vectors, whose values are optimized through stochastic gradient descent. This implementation reduced rendering time from several hours to several milliseconds, which enables real-time interaction with NeRF scenes. The Fox video here shows the real-time optimization of NeRF in under 5 seconds. There are attempts to use NeRF to solve real-world problems. In February, Waymo released BlockNeRF, which used NeRF to map large environments. In April, a paper provided a concept of navigating robots using NeRF depth estimation. Currently, extended reality environments we experience using HMDs are generally 3D rendered environments. For applications like remote collaboration, where we need to share new world environments as quickly as possible, this becomes a bottleneck because reconstructing a real-world environment in 3D is both time-consuming and labor-intensive. There have been approaches to overcome this problem, for example using 3D cameras or sharing point clouds of the environment. However, the environment shared was not of a quality to feel immersiveness. We focused on NeRF's exceptional ability to synthesize novel views photorealistically and wanted to do a proof of concept of sharing a real-world environment using NeRF. The ability of NeRF is astounding. It can produce excellent novel views of complex scenes with photorealistic quality. No pre-processing is necessary other than taking a video of the environment. The model generated by NeRF itself is very small in size, about 50 megabytes. There are multiple roadblocks if you want to use NeRF to share environments, though. Ideally, we should be able to send the model itself to the HMD and let it create novel views itself. However, the process is very compute intensive, in which, with the most high-end graphics cards such as the NVIDIA A100, we are only able to generate about 10 frames per second in full HD resolution. Adding an object to an already optimized scene is hard. We can't make modifications to the rendering pipeline due to the nature of volume rendering. To overcome this, we designed a cloud-based distributed NeRF rendering environment called InstantXR with multiple cloud renderers. We combined the traditional 3D rendering method with NeRF's depth estimation to place an object in the environment generated by NeRF. To send the remotely rendered scene to the client, we designed a novel streaming method which is simple and achieves very low latency. We also devised a method to share head position, also with low latency. The platform is 100% compatible with the current web standards, so there are no requirements to the client other than a web standards compliant browser. With this architecture, all you need to do to share an environment is to take a video of it. The NeRF implementation will use an algorithm to extract frames with good quality and focus, and run a structure from motion or SFM algorithm against it. With the spatial location and viewing direction data from SFM, along with the image, the NeRF network optimizes the environment in under 5 minutes and is able to generate high-quality novel views. When the NeRF network is ready, the user can experience remotely streamed novel views using untethered HMD. There are no requirements to the HMD device other than a web standards compliant browser. Rendering a scene remotely to an HMD is not a trivial task. You need to receive the head position, render the scene, and send it back to the HMD. The loop should be very fast or VR sickness will occur to the user. We were rendering not only remotely, but also distributed due to the slow rendering process of NeRF. To output at least 80 frames per second, the low threshold in which VR sickness does not occur, we created a cloud encoding server which controls the whole rendering process and the cloud renderer that renders a scene. The server pairs with multiple cloud renderers to parallelize the rendering process, thus generating more frames. It was not easy to implement this structure. We had to come up with a scheduling algorithm that governs the whole process. Because the rendering time of NeRF is different for every scene, we had to drop frames that are creating a bottleneck due to its slow render time. Distribution of frame render requests from the server to the renderer should be done considering the metrics. Order of the frames should be honored strictly because of the different render times. XR devices have stereoscopic displays, so we had no option but to implement capability to support multiple render targets to generate 2 video streams. Because we had so many factors to consider and optimizations were a must, we had to use C++ language to program our server and renderer to access low-level APIs of FFmpeg, a video handling library we used. It is of utmost importance to send the remotely rendered scene to the user as fast as we can. However, we faced difficulties in choosing an appropriate streaming protocol to transport the stream to the client. Streaming protocols typically focus on latency, reliability, or scalability, and to achieve the goal, they generate delays. Because delays are unacceptable in our use case, we devised a streaming method that rapidly streams video packets to a client without introducing any delay. Once the client receives the packet, it is decoded and instantly shown to the user. Because we don't need to stream audio and do not have to honor the time between each scene, there is no need for any delay for synchronization. Although this method is not the best to implement instant streaming, it is by far the easiest and web standards compliant way to achieve promising latency and quality. NeRF uses volume rendering and outputs a scene as an RGB image. If we were to place an object in the area shared with NeRF, it is impossible to do so using the scene image. However, because NeRF estimates the volume density to determine the color of the scene, we can get the density information along with the RGB scene. Using this, we can perform depth testing between the depth buffer of legacy 3D assets and the estimated depth from NeRF. We compared the depth information from the NeRF renderer with the depth buffer of an object rendered through the conventional 3D renderer. As you can see, NeRF can estimate the depth pretty accurately, and there is no problem placing the torus between the chair and the trash can. Of course, the estimation of depth is not perfect. NeRF has trouble estimating depth on surfaces with diffused reflections, while it performs best on matte surfaces. So, without further delay, I'd like to present a demo video of our architecture in action using 8 renderers. We used InstantXR to share the living lab in Korea Institute of Science and Technology to my home using videos taken from the lab.
Maybe you can comment the video. Can you hear me? You can take the microphone if you want. You have to open your microphone. Maybe you can comment a little bit. cannot hear you. Can you take your microphone, please? T'entends pas.
Okay. So our proposed method can provide a mirror world as an immersive XR environment without the cumbersome modeling process. We can combine 3D assets into the generated world without any issue. Unfortunately, the high computational power requirements of the current NeRF structure and implementation makes it difficult to design a scalable solution for our proposed system. We do not believe our current structure could scale. However, the growing research and development in the neural rendering fields makes it possible to envision the not-too-distant future where mobile GPUs will be able to render NeRF scenes directly. We expect the experience and errors faced in developing our current proposed system and structure will provide guidance in the future. In future work, we will further evaluate our method along with mesh models and point clouds and find a suitable method for InstantXR services. Along with the evaluation, we will find ways to improve user experience, most importantly, lowering latency, but improving judder control or noise reduction of head position. Furthermore, while there is research done to improve motion-to-pothon latency, or MTP latency, in 3D rendering environments, improving MTP latency in volume rendering environments is not studied often. We plan to explore ways to reduce MTP latency, in particular where volume rendering is used based on remote user input. This has been the presentation for InstantXR. Thank you for the privilege of your time. If you want to learn more about our system, please visit the link below.
Now we have some time for questions, but there is a problem with the microphone. Can you check the microphone and try to speak? We have allowed it from here, but can you open your microphone? It doesn't work.
Hello, can anyone hear me?
Yes, perfect.
Thanks. Firstly, thank you all for listening to my presentation. One thing to note is that I've tried very hard to lower the latency of the environment, but it seems that the remote streaming of the video, not the platform, has made it look like it has huge latencies, but if you check the YouTube video provided in the link,
yes, I think it's okay. We have the link.
the latency that the platform is having.
Okay, thank you. So maybe there are some questions here or in the chat.
Okay, so what someone has asked me, can you describe what we are seeing? And you are seeing a laboratory at the Korean Institute of Science and Technology. From my home, I am experiencing the laboratory with my HMD, but the laboratory is not 3D constructed or in any way. It was streamed real time with a model that has been learned with the laboratory scenes. So we can say that it is generated by NeRF. Because HMD does not have the capability to render NeRF, the NeRF renderer was in a remote server, and the HMD has actually received my head position and viewing result, and the server received my head position, rendered the scene, and sent it back to me, and I am seeing that video.
So you mean that the 3D point of view is controlled by you with your head-mounted display in your place, and you visualize the 3D scene, the remote 3D scene with your method. The tracking is done locally in your home, and the point of view is changing according to your movements. That's what you expect. Okay. Very interesting. I think it's a very, very innovative idea and clearly very new.
Thank you so much. Mr. Birchman asked me that whether
there are some other questions. You can see them on the chat. So okay. I give the floor to the question from Donald. Oh no, from Donald first and Marius.
Okay. Should I select the questions or?
Yes, from Donald. You can see it. The question.
Okay.
Is about your is your resulting 3D model eventually saved as a file? Is it possible to share those files for repeating this important work? Thanks for impressive contributions.
Okay, so thank you for marking my contribution as impressive. And so it is not a 3D model, actually. It is a neural network that has been optimized to render that particular scene. So it is not a 3D model in every way. If it was a 3D model, we would have be able to place a torus without depth testing in any way, but it is not a 3D model, so it outputs an RGB image from the neural network. So so that's one, and the network, of course, can be saved, and the size of the model is actually quite small. It's about 50 megabytes, and I will be sharing the resulting NeRF model in my GitHub repository that saves the file, that hosts the code.
So what is registered? What is it a file or is it the network or what do you?
It is saved as a file, which is saving the parameters and values of the network.
Okay. Yes, parameters. Okay. The second question is from Marius.
Yeah, maybe I can explain it better. So now your network is able to generate the videos, the images of your office. How dense the captured video images are that you use to learn the model?
The video, well, to be honest, if we were to use the implementation from NVIDIA without any modifications, we will be inputting a video taken from the lab, and an algorithm will pre-process the video to get best frames, but of course the frame would be all random because the algorithm cannot look for frames that the NeRF network needs to know. So I've handpicked the frames from the video and trained the network with those images. And the images, so those are images, and the images themselves were about 60 to 70 photos. I can't remember the exact count, but it was 60 to 70 images, and the images were very, I can't remember the exact term, but I took every nook and cranny of the laboratory.
So somehow you ensured that you captured all the data. You tried to cover the entire space.
That is correct, but I failed to cover the environment 100%. So if you see the video, when I turn my head to the top, there are some places that NeRF fails to render. Or if I see the bottom, there are some places that NeRF fails to recognize because the floor is reflective and NeRF can't determine whether this is a surface or not. I'm sorry, can you repeat the question? I think
we are out of time, so we want to thank you again for this very interesting presentation. And again,
thank you all for.
And we are going to listen to the next speaker, who is remote, I think. So the presentation will be done by Julian Croci. And the title of the presentation is Terrender, a web-based multi-resolution terrain rendering framework. So, Julian, it's up to you.
Yes, can you hear me?
Yes.
See the presentation. Very good. My name is Julian Croci, and I welcome you to the presentation of the web-based multi-resolution terrain rendering. Terrain rendering is a fundamental component of applications. Our goal is to create an open source terrain renderer that runs on such as mobile phones is in the browser. The handling of large datasets should be possible visual fidelity of the rendered terrain should be high. Especially, we wanted to avoid visual discontinuity. There are different techniques for multi-resolution terrain rendering, such as VDAM or AM raster. We decided to use raster. At the core of the render is the raster algorithm invented by Bush et al. In 2000. Operates on regular grids to hide data. For example, no meshes and are easy to browse environment. Further, raster is able to faster create a terrain mesh based on the camera. One way of rendering 2.5D terrain data is to create a flat triangulated mesh. Then displays the vertical height map. The mesh can have a higher triangle count closer to the that is needed. The height map can also have a higher resolution. These triangles can be easily stored in trees. The eventually created binary tree is not as the highest resolution. It is important that no hanging vertices, respectively junctions, occur in the mesh, as the plane is not rendered continuously, might have cracks that are. Faster, the B tree is created top-down. Every node error metric.
Julian?
Yes?
Julian, we have a problem in understanding you. I don't know if it's the network connection or your microphone. If you can keep it closer to your mouth. So we have the video, that is no problem, but the audio is not very fluid.
Okay, I will try. Is it better now?
Is much better if you, but yeah, maybe even take it, keep it in your hand is even better.
Okay.
Okay, thank you.
No problem. Okay, so then in raster, the bean tree is created top-down. For every node, an error metric is evaluated. If the value of the error metric is above a threshold, the node is split, as it is not split. This creation of the bean tree is essential to avoid hanging vertices. In raster, each triangle is evaluated by the center point of the hypotenuse. Since two neighboring triangles share this point, either both of them are split or not. Therefore, T-junctions are avoided. Neighboring triangles hence mean triangles sharing the hypotenuse. Further, it is important that the neighboring triangle exists, as it could not be split. One option would be to look up the neighboring triangle in the bean tree. However, the neighboring node is not a sibling in the bean tree. Hence, this lookup is costly at runtime. Instead, the error metric can support the so-called saturation condition described by Olberg et al. In 1999. This condition guarantees that the neighboring triangle will also eventually exist and also be split, as the reference point is the same on the hypotenuse. These bean tree nodes in the raster algorithm do not represent single triangles, but a group of triangles, so-called K-patches. K-patches allow a continuous transition between different levels of detail. And, more importantly, they reduce the size of the bean tree that has to be generated significantly, which allows it to run fast in the browser. The data in raster is stored in a quadtree. The quadtree represents a pyramidal structure, where each node represents a square texture with the same size, a so-called M-block. With each new level in the quadtree, the pixel density is doubled. A bean tree node uses part of the data of one quadtree node, but a quadtree node contains the data for different K-patches. The bean tree nodes belonging to the same quadtree node can also be in different levels in the bean tree. For our implementation for the error metric, we used the octagon metric described by Gerst in 2003. However, other metrics could also have been used. The octagon metric satisfies the saturation condition by considering octagonal bounding volumes whose center is at the middle of the hypotenuse. The combined error metric in Terrender is based on 3 single metrics. The distance metric is dependent on the camera position. The closer the camera is to the refinement point, the higher is the value of the metric. The second one is the culling metric, which is 1 if the bounding shape is in the view frustum and 0 otherwise. The third one is the geometry metric. It is based on the roughness of the terrain. This means that its value is higher the rougher the terrain is in that area. These error metrics can be combined via multiplication. And as all metrics are saturated, the combined metric is also saturated. This guarantees that the created mesh is continuous. We extended the geometry error metric as it needs to be created beforehand, as the data is not available on the client when creating the bin tree. The geometry error is given by the difference between the min and the max bound of a bin tree node. Simplified said, the minimum and the maximum value in the area that is of interest for the current node. It is created bottom up to guarantee the saturation condition. And the min-max bounds of each node are defined by the min-max bounds of its neighbor and their children. Now I will provide an example how the max bound is pre-calculated. The min bounds are derived similarly. Below the leaf nodes in the graphic to the left, the maximum values in the covered area is written. For the leaf nodes, the max bound is given by the maximum of the values the node covers and the maximum values of its neighbor. As can be seen in the graphic, neighboring nodes might be far apart in the bin tree. Hence, the neighboring nodes have to be found. The next level is defined by the children of the node and the children of its neighbor. This is continued until we reach the root of the tree. The result is then saved in a JSON file for Terrender to use. To save space, subtrees where the difference between the min and the max bound is 0 can be removed. Also, it is possible to define a custom threshold below which subtrees are removed from the bin tree. However, in this case, information is lost, meaning that the geometry error is less fine-grained. But the metric is still saturated in that case. Now we come to the implementation of Terrender. First, I give an overview over the whole system. At first, we have the pre-process step, which creates the M block for the quad tree from the raw height and color data. The color data is optional. Further, the geometry error can be optionally calculated from the height quad tree. Then we have a very simple backend. It serves the Terrender website, so the HTML, CSS, and JavaScript code. And at runtime, it serves the geometry error, if available, and the requested height and color data for the quad tree. The implementation is mostly independent from the front end. For our implementation, we used a simple Node.js server. The front end is the most complex part of Terrender. First, we have the mesh updater, which creates the current mesh based on the camera parameters and the geometry error, if available. Then we have the data manager, which requests new data from the server and manages the caching of already loaded data. Once we have the data and the mesh, the WebGL renderer renders the terrain, also meaning the collection of K patches that create the terrain. Now I will give an overview over the render loop of Terrender. However, it is not really a loop, but a method that is called by the browser whenever the browser considers to draw a new frame. This method runs in the main thread. First, it is checked whether the camera moved since the last frame. If this is the case, it is checked if no data is already loading from an older mesh creation. If no data is loading, we update the bean tree representing the terrain mesh. Together with the bean tree, the quad tree is updated. The quad tree manages the data required to render the terrain mesh. Then we start loading the newly required data from the new terrain mesh. The loading of the data happens in parallel to the main thread and will likely take multiple frames as the required data can be quite large. Hence, we already render the terrain with the new camera parameters, but the old terrain mesh we still have. Otherwise, the user would not be able to navigate smoothly through the terrain. If already data is loading from a previous bin tree update, nothing is done except the redrawing of the terrain with the new camera parameters. Else we would have to risk to congest the bandwidth with outdated cars, leading to a race condition, and the terrain mesh will maybe never be updated. If the camera has not moved, we check if the previous data requests have finished loading. If this is the case, we update the bin tree once more, as the camera might have moved since the last terrain mesh update. If nothing changed at all, the terrain is not redrawn, as nothing would have changed since the last frame. Now I will explain how the asynchronous data loading is implemented. Note that this is on the level of a single M block. However, all M blocks need to be finished loading before the new terrain mesh can be rendered. Most operations in this step happen in parallel to the main thread. However, sometimes a callback on the main thread is invoked. I start with the explanation of the async data loading for the height texture. First, the height data is loaded. Once the data has been loaded from the server, a callback on the main thread is executed. This callback hands the raw data over to a web worker. In this web worker, the data is parsed and prepared. Once the web worker finished, it hands the data back to the main thread. On the main thread, another callback is invoked that loads the data into the GPU memory. As these steps are individually executed for each M block and take a different amount of time, the connection to the GPU memory is less congested because it is distributed over a time frame. After loading the height data to the GPU, the loading of the height has finished. Now I will explain the loading of the color data. This is simpler as all browsers can handle normal images directly. So once the color data has been loaded, it is loaded to the GPU and the color loading step finished. Loading of color and height data happen in parallel. When both finished, the M block is ready for rendering. Now to the data management on the client. For data management, the quadtree nodes, so the M blocks, are organized in lists. The first list is the render list. It contains the M blocks whose K patches are currently rendered in the terrain mesh. Second, we have the future list, which contains the M blocks that are in the terrain mesh that will be rendered next. This list contains M blocks that are currently being loaded, but it can also contain M blocks that are already being rendered, hence also in the render list. The third list is the on-GPU list. It contains M blocks whose data is currently on the GPU memory, but that are currently not rendered. The fourth list is the on-RAM list. It contains the M blocks whose data is currently on the RAM. When all blocks in the future list finish loading, the future list becomes the render list. The M blocks of the render list that are no longer rendered are added to the end of the on-GPU list. Then the length of the on-GPU list is checked. In this example, we assume that the on-GPU list should be maximally 5 long. The nodes at the front of the on-GPU list are then added to the end of the on-RAM list until the on-GPU size is 5 in this example. The data of these nodes is removed from the GPU memory. Then the length of the on-RAM list is checked. In this example, we assume that the maximum length should be 3. As the on-RAM list exceeds the limit, the nodes at the front of the on-RAM list are removed from the list and the data is deleted until the list length matches the max length. This gives implicitly a cache that operates with the first in, first out caching strategy. As we use doubly linked lists, the nodes can be fastly moved from one list to another. Now I will present an extension we made to the raster algorithm. As the time between terrain updates can be quite long, especially during long camera trajectories. The terrain mesh rendered at the time can be suboptimal for the camera parameters at that time, because it might be based on a camera position a long time ago, respectively far away. To reduce this problem and increase the visual fidelity during long camera trajectories, not the entire potential bin tree is created. This leads to the fact that the maximum level of detail is decreased, but the overall level of detail is better adapted to the current camera position. We achieved this by first creating the beam tree as normal in a breadth-first manner. When a level in the beam tree would be created that would be mapped into a new level in the quad tree, we first check the ratio between not loaded required nodes and required nodes. If the ratio is below a threshold, we continue with the beam tree creation. For this example, we define the ratio to be 0.6. In this case, we have one required M block that has already been loaded, and hence the ratio is 0, and we continue. As we continue the creation of the beam tree, we hit another new level that would require a new level in the quad tree. Once again, we check the ratio. Now we have 4 required M blocks, of which 2 are not yet loaded. Hence, the ratio is 0.5. And as it is below 0.6, we continue. The creation is continued, and once more, we hit a new level in the quad tree. Now, 15 M blocks are required, of which 10 are not yet ready. This calculates to a ratio of 0.6.7. And as this is above the threshold of 0.6, we stop the creation of the beam tree at this point. The beam tree is then used as normal. The beam tree will be re-evaluated once the data has finished loading, but then possibly with new camera parameters. Now I will show Terrender in motion and some of the benchmarks we did. First, I want to show you a camera trajectory without any bandwidth limit. Hence, the terrain is rendered with a very high quality throughout the trajectory. All videos were recorded on a MacBook Pro M1 Max with 64 GB of RAM using the Chrome browser. This trajectory without a bandwidth limit is a good benchmark for the efficiency of the client code, as the bandwidth is less a bottleneck. Hence, we tested Terrender on 3 different browsers, Firefox, Safari, and Chrome, without a bandwidth limit. On all 3 browsers, the framerate was mostly stable and the program was usable. Of the 3 browsers, Chrome performed the best. The framerate was always smooth and hardly ever changed. Firefox performed a little bit worse. The framerate was mostly smooth but less stable. Also, a few notable frame drops happened. Safari was the least stable with occasional and notable frame drops. However, the frame rate was mostly high enough to use the program. This shows that the performance of Terrender is very dependent on the browser being used. Next, I will show the influence the dynamic update extension has on the visual fidelity during a long trajectory. In this case, we limited the bandwidth to 40 megabits per second. On the left is the trajectory without dynamic updates, on the right with. As now at this point can be seen, the visual fidelity is higher on the right, where the dynamic updates are activated. We also investigated how the dynamic updates affect the updates of the terrain mesh during this trajectory with limited bandwidth. The data points in the plot stand for updates of the terrain mesh during the trajectory. On the x-axis is the time in the trajectory, on the y-axis the depth of the quad tree that has been created at this timestamp. Note that the maximum quad tree depth for the used dataset is 9. As at the start, many updates with high depth can be seen, as the data from the initial render can be reused. The longer the trajectory goes, the less frequent are the updates, and the depth of the quad tree decreases, because the amount of newly required data increases. Also, we compared Terrender with Cesium.js. Cesium.js is a well-known open source front-end framework that has been developed for a long time and provides a wide variety of features. For the comparison, we only focus on the terrain rendering component of Cesium.js. Cesium continuously updates the terrain during trajectories, which can result in discontinuities. To compare Cesium.js and Terrender, we programmed the trajectory in Cesium.js to only move the camera to the next position where it should be on the trajectory at the current timestamp. No more data is being loaded. This means when the update finished. On the chart, we see when full updates for both Terrender and Cesium happened. Note that we disabled the dynamic update extension of Terrender for this test. As can be seen, updates to the terrain happen similarly often. However, Terrender always has a continuous terrain, while Cesium.js might produce some cracks and discontinuities. So with this, I am at the end of my presentation. I hope you enjoyed it.
Thank you. We have a few minutes for questions. So for this rendering, are there more differences? Because can you show again your last slide, the comparison between Cesium and Terrender? Because could you comment a little bit the updates?
So yes, we have at the beginning of the, you can see my mouse, right? So what we did is we wanted to check how much time passes between two updates, entire updates to the terrain in both Cesium and Terrender. And what can be seen is that at the start, these updates happen fairly often. So we have the green dots here for Terrender with nearly updates every few frames, and those for Cesium. And then as it prolongs, we see that the updates happen roughly at the same time. But we also see that the time between updates increases, meaning that the current terrain mesh, so the fidelity of the current terrain mesh, is likely less adopted to the current camera position.
Okay, thank you. There is a question from Lewis Spencer. Can the terrain rendering handle overhanging geometry, or is it only a height map?
No, it can not handle overhanging geometry as it works with height maps, so regular grids currently.
Okay. And there is also a question from Donald. Are videos and project online? I think that if it is possible, you could share it in the chat, or maybe later. I don't know. It would be interesting.
Yes, I think the videos are online on the ACM page. Can the video be found? So the comparison videos and everything. And I will also post the link to the GitHub repository.
Okay, thanks a lot. Okay, thanks very much. And I think that we're going to the last presentation now.
Thank you too.
So the last presentation will be made by Tony Tan. It's about a framework for safe execution of user-uploaded algorithm, and it will be our last presentation. Thank you to be here, and it's up to you now.
Test. Yeah. Okay. Thank you very much for the introduction. My name is Tony Tan, and I'm from the University of Bremen. Today, I would like to share a little bit about our framework. The main idea is how can we safely execute user-uploaded algorithms in the context of benchmark as an online service.
It seems.
Okay, I'll continue. I'm sorry for the. So as we may agree, benchmarks are important to measure the progress in the scientific community. However, it is not always easy to replicate results from the existing papers. There could be many reasons behind it. For instance, the instruction is missing, the data or the codes are missing, or maybe some hardware or software are incompatible. In the computer graphics, there are some studies by analyzing paper from SIGGRAPH 2014, 16, and 18. And they found out that only half of the paper comes out with software packages. And among of those software packages, only half of it can run out of the box. Some of it needs some sort of modification to work, and some of it could not even produce the same results as reported in the paper. And all of these issues can actually be solved by open benchmark. It is not only reproducible, but also at the same time make the results comparable as well. Such open benchmark need to satisfy following requirements. First of all, the results must be reproducible and comparable. The best way to achieve this is by running the benchmark under the same hardware and software environment. And second, it must be easy to use in the sense that it doesn't need to require extensive knowledge about the benchmark itself to run the benchmark. And lastly, such benchmark must be sustainable in the sense that when the new hardware or software comes out, the existing algorithms should be continuously updated to work. For instance, by notifying the author of the proposed algorithms. One way to provide such open benchmark is by offering benchmark as an online service. Such service is already exists, for instance, for the collision detection algorithm as proposed by Open Callbench. The architecture of such benchmark as an online service, in this case, the Open Callbench separated into two parts, the front end and the back end. The idea is to prevent any process, such as user interaction at the front end, to actually affect the benchmark results done by the back end. The front end of such system is an easy-to-use interface where the user can upload object, select parameter to benchmark. It's very intuitive. And as a result, the user will get not only a plot of the benchmark results, but a visualization of the benchmark result itself, which could help to better understand how the algorithms actually behave. In this example, we can identify that in this particular algorithms, if the collision occurs around the ear, then it is slow. One challenge of such system is the integration of the new algorithms from users. Currently, to integrate new algorithms, it is sufficient for user to compile the algorithms into the wrapper DLL. However, directly executing such unknown codes will expose the system into the risk. One might thing to analyze and validating the code just before the execution, which is not trivial. Even if it is possible, it will still put the system into the risk. The current integration is manually done by the administrator, which is not only time consuming, but also problematic. For instance, in the case of work in progress development or non-disclosure agreement. To solve this challenge, in this paper, we propose the idea of running the user-uploaded algorithms into the virtualization environment. Not only this guarantee the security of the benchmark, but also at the same time, the reproducibility and comparability of the benchmark. In our framework, the entire process from running the benchmark into virtualization environment is automated as well. To apply the idea into the existing framework, in this case, the open call bench, we extend the existing system by moving out the benchmark into the virtualization environment. And in addition, we also add a WebSocket to communicate with the virtual machine when the benchmark, to get the results when the benchmark is done, since a classic HTTP request will time out in this case. The WebSocket will communicate with the Hyper-V to automate the benchmark process from turning on or turning off the virtual machine to resetting virtual machine to the initial state. Currently, Hyper-V is our choice of virtualizations since it supports SIMD instruction set and GPU, which is required by some algorithms like SIMDOP. However, in this case, any virtualization will work as well. To some extent, depends on the requirements. To provide the security guarantee as well as the comparability, currently we only allow one virtual machine to run at one time. This is beside the comparability. This is also to prevent user from overloading the host system by simultaneously sending requests to benchmark at almost the same time. After the benchmark, the virtual machine will always reset back to the initial state before starting a new benchmark job. The idea is to prevent any system change by either operating system updates or made by the previous algorithms. Here is a quick demo of our implementation. On the bottom left is the console output of the backend and the WebSocket server. On the right side is the easy-to-use interface where user can easily upload objects and select algorithms to benchmark. The user-selected parameter will be then sent to the backend, which will then instruct the WebSocket server to start benchmark at the virtual machine. Once it is done, the results will be sent back to the backend, which will then generate the visualization of the benchmark results as a heat map and send it back to the user browser where you can user can actually interact with it. Although, even though the benchmark system is, as we can say, completely safe, one question might arise. Is the benchmark results from such virtualizations is actually reliable as well? To answer this question, we did some tests by using the same benchmark parameter in both native and virtualization environment. Here are some objects that we use in our tests. Every single one of these objects has a different size of polygon counts from a few thousands to up to 120,000. For each object, we generate around 200,000 different configurations. Configuration in this case means the relative position and orientation between objects. And we generate these configurations at a distance zero. Distance zero in this case means the objects are very close to each other, but are not colliding. The benchmark itself for each object takes up to 20 minutes to finish, depends on the objects and algorithms. We also run the benchmark using common collision detection algorithms. For instance, the DOP3, box3, PQP, VCollat, and SIMDOP as well. Back to the questions about the reliability. First of all, we compare the benchmark results using different CPUs. In this case, we use the AMD CPUs and Intel CPUs. On the left side is the results from the AMD CPU, and Intel's the right side is the results from the Intel CPUs. The number of the object polygon is shown by the x-axis. The y-axis shows the average running time of a single collision check in milliseconds. As expected, due to the extra virtualization layer, benchmarking in the virtual machines is slightly slower compared with the native environment. However, the results from both CPUs in the different environments show that the delta remains consistent across different algorithms, object shapes, and complexities. Another interesting question to answer is how reliable is actually the results when using the SIMD instruction sets. In this case, we did a test using the latest AVX 512 for the SIMDOP algorithms. SIMDOP in this case is the only algorithms that make use of the SIMD instruction set, as we know. In this case, we only run the benchmark using Intel CPUs, as AMD did not support the AVX 512 at the time when this paper is submitted. On the left side, we have the results from the object hand, and on the right side from the object castle. As we can see from the results, the delta is also consistent across different object shapes and complexity as well. So far, we run our benchmark on virtual machine using only one core and see a small delta from the results. One might suspect that the operating system process could probably affect the results by doing something during the benchmark process. Therefore, we tested whether multi-core system in virtual machine will affect the running time. For this purpose, we tested virtual machines with 1, 2, and 3 cores. And our finding is that the multi-core does not affect running time at all, which means the delta from previous results are purely due to the extra virtualization layer and not caused by any additional process by the operating system. Besides average running time, it might be also interesting to see whether every single collision check are reliable as well. In the previous slide, we have the results based on the average of the running time. This can be done by visually comparing heat map from both environments. Here we have the results from the box tree in native environment and virtualization environment. And the results looks very similar in our test. We also have another results from another algorithms, in this case the VCollat, which also looks very similar as well. Therefore, we can conclude that although there exists delta due to the extra virtualization layer, running benchmark in virtualization environments is not only safe, but reliable as well. To summarize, we presented a framework for a secure execution of user-uploaded algorithms in virtualization environment. The entire process is automated using PowerShell script and implemented on top of existing benchmark. As an online service, namely Open Callbench, we show that not only we can guarantee the security of such system, but also at the same time the results are reliable as well. One interesting part for the future work is probably the implementation of REST endpoint at the backend system. This will allow user to automatically benchmark their application within continuous integration pipeline, or as a plugin for IDE, such as Visual Studio or the Visual Studio Code, so that the authors can directly assess the effects of change in their algorithms during development. Thank you for your attention. Feel free to ask me if you have any questions.
Thank you for your presentation. Do you have some questions?
Thank you. This is great work, and I can see it being very valuable to our field. Reproducibility is essential for scientific progress. If I understood correctly, you are testing a set of algorithms which are essentially bounding volume hierarchies or some kind of geometric analysis. It occurs to me that there might be some, I'm curious what you think, other possibilities for the benchmarking as a service. For example, testing some executable shaders to look at differences in appearance, perhaps. Or if we have an interactive object, trying lots of user event combinations to see how they're working. I'm curious, do you see any possibility there?
Yeah, thank you for the question. I think that's possible, actually. I think we can, in my opinion, we can take the idea of benchmark as an online service, not only for collision detection, but also other applications as well. The reason why I chose the collision detection is because I did a lot of work with the collision detection. And at the time, I found out that some papers that are quite old, like decades old, it's not working anymore, which is quite sad in my opinion. And like if I may borrow your word from today, we are kind of like reinventing the wheels again.
Yes.
So I think I would like if to see if we can take this idea into other applications, and yeah, maybe we can preserve the results at the same time.
Yeah, it's excellent. Would there be? You mentioned the GPU, so I'm curious about, would any of the requirements change if we moved from the problem of collision detection maybe to reproducible shaders or programmable graphics? Maybe you don't need the SIMD instruction set anymore, but the GPU would be more important. I don't know.
Yeah, I think that's possible. I think that's the idea remains same. Benchmark as an online service, but the requirement could change, depends on the application.
Yeah.
It doesn't need to always have the SIMD. It doesn't need to always have the Hyper-V. I mean, if Docker is enough, then you can use Docker as well.
Right. Okay, great. Thank you.
Thank you. Other questions?
You say you're running an application one at a time. How do I know that you've got something running, or do I have to go through you first before I can do this, or can I just upload it, 2 a.m. my time and it's perfectly fine because Europe's asleep or something?
Yeah, we actually have a student that's still working on this. So we basically implement some kind of queue system to make sure that only one virtual machine run at a one time. So basically the idea is you can upload your objects, select the algorithms, and you come back later and you got your results. The queue system will take care of the entire running.
Okay. Other questions? So I think we can stop now. Thank you to all the authors. And thank you to the participants here and at distance. And I think that now we have lunch.
Yeah, now we go for lunch. So follow the people that knows where the lunch is. If you have some constraints and you are vegetarian or you have some special regime, don't hesitate to tell also to the registration desk, and especially also for tomorrow evening. It would be to know in advance if you are vegetarian or other constraints. Yeah, just talk with them and they will take a note. Okay, let's have a lunch. After lunch, it will be here again at 1.